Hi, I'm Beth Faber from the Hydrologic Engineering Center, and this is part one of the lecture on coincident frequency analysis. This is the 12th lecture in the course on statistical methods in hydrology. So sometimes I need to estimate a probability distribution for a variable that I don't have any observations for. Right? Maybe I don't have a gauge where I need it. Maybe it's a situation that actually doesn't even exist yet, but is only proposed. So maybe this variable is related to another variable for which we do have observations and can estimate a probability distribution. So maybe I can do some modeling to transform from the variable I know about to the variable that I care about. Right? But maybe the variable I care about is actually dependent on more than one other random variable, right? Each with probability distributions. So this is a multivariate problem, right? So I need an approach for combining the probability distributions for the variables that I know about and the response of the variable that I'm interested in to those other random variables. Okay, so coincident frequency analysis, another way of saying joint probability, and we're looking at the likelihoods of several different processes because all of them affect a single variable that we care about. Right? So sometimes the occurrence of interest is dependent on two or more other processes, and to estimate the probability that we care about, we have to bring together the probabilities of the other processes that influence it. So I'm going to talk about two different approaches in this lecture. One is the total probability method, known in our Corps of Engineers guidance just as the coincident frequency analysis method, and the other is Monte Carlo simulation. Right now, the total probability method approach is based on two random variables informing a third that we care about. If we have more than two variables, if we have three, sometimes we can do the analysis once to combine two of the variables and then do it a second time to combine the third. But I'm going to walk through problems first with just two variables. So here's some examples of problems that we might use this type of analysis for. These are the two most common. On the left, we have an interior flooding problem. So we've got a levee built along a channel to protect an interior area, but at the same time, it also blocks drainage from the interior area into the channel. Right, so we have to do something about that. And maybe we have a pond at a low area, and we've got some gravity drainage through the levee into the channel, and that drainage is maybe blocked by a flap gate at times when the channel is high, right? So we don't allow flow back in the opposite direction. And maybe we've got some pumps here that we want to design for getting water into the channel in those situations. So here, the variable that we're interested in, variable C, is going to be the stage in the pond behind the levee. And that's going to be influenced both by flow from the interior and also by flow or stage in the channel. Right? The problem on the left is a tributary flooding problem where we have some damage area on a tributary near a main stem, and the stage at the tributary is of interest, and that's going to be influenced by both the flow on the tributary and the flow or stage in the main stem. Right? Here's a similar problem where we have flow into some body of water. Right, so we care about stage here at C, and that's going to be influenced by both flow on the river and stage in the ocean or lake. Right, on the right, we have a reservoir providing some flood protection, and maybe we want to size the flood control pool, or maybe we already have a defined flood control pool, but we want to know the probability distribution for the peak stage from flood events, right? So in this case, the variable of interest is going to be my annual peak stage, C, and it's going to be influenced by the flow into the reservoir and also by the starting storage in the reservoir during each flood event. Okay. Now this one was added by Stan Gibson, who came to HEC from the Buffalo district. And in the Buffalo district, they have ice jams. And he added this picture of Cazenovia Creek in South Buffalo because I had never seen an ice jam before. So yes, ice jams are a problem in Buffalo. So here the variable of interest is the stage on the channel, and that is affected by the conveyance reduction due to ice, and then of course the flow in the channel. And then the last example I'm showing is a combined runoff and storm surge situation. So we've got our desired variable is the estuary stage, and that's influenced by both the storm surge and then also runoff happening at the same time. So to describe the theory and the questions we're going to ask, I'm going to walk forward with the tributary flooding example, right? So in this case, this is where we wanted the stage frequency curve at C, and this is influenced by both the tributary flow A and the stage on the main stem B, where this stage might cause some backwater up the channel. Right now, if I have any particular level of A and B, then hydraulic modeling will allow me to compute the stage at C. This allows me to define the response of C to A and B. Right, so let's look at that situation more closely. Here's a view from the side. Here's our tributary channel. Here's our main stem. So for a given flow on the tributary and a given low stage on the channel that doesn't produce any backwater effect, then I might have this stage at C. On the other hand, if I have this same flow, maybe a 100-year flow on the tributary, and at the same time I have a much higher flow on the channel, maybe also a 100-year flow on the main stem channel, then I'm going to have a much higher stage at C because of the backwater effect. Right? So I can't just transform my probability distribution at A to a probability distribution at C because B has an influence. Right? Now, it's also important that if I have a lower flow on A, I can get the same response at C for some higher value of stage in the tributary. Right? So there's a little bit of backwater maybe, but not as much. So if I'm interested in the probability of different outcomes at C, it's very important that any given outcome at C can be produced with different combinations of flows at A and stages at B, right? So a particular outcome at C is more likely if there's different ways that I can produce it. So to evaluate a probability distribution at C, we need to be aware of and combine the probability distribution at A, the probability distribution at C, and the response at C from all possible outcomes at A and B. Now, I didn't just assign these variable names randomly. My variable C is the variable of interest. In this case, it was the stage on the tributary where there might be a damage area. And variable A is the more influential variable, the one that has more influence on C. And variable B is the one that has less influence. So in that case, the annual probabilities at C are going to be based on annual extreme probabilities at A, right? And not necessarily the annual extremes at B. So one way to approach this problem might be to assume worst case, right? So in problems like the interior flooding problem, we could just assume that the gravity drain is always blocked, right? A worst case situation. And that would make the problem a lot more simple to evaluate, and it's conservative, right? But what happens if we assume a worst case? Well, the problem is that we mess up the probabilistic description, right? Because we've attached a condition. Saying that the gravity drain is always blocked is a condition applied on variable B, right? And so if we were modeling the 100-year flow at A and expecting to get a 100-year stage at C, what we get is not actually a 100-year stage at C, right? Because we've attached this condition, and this condition doesn't have a probability of 1, right? So the resulting probability at C is actually less, okay? So we no longer have an accurate probabilistic description, and we need to find a way to incorporate all these probabilities, right? So what assumptions are we going to make about the flood event on the tributary and on the main stem? Well, it's going to depend on whether we see flood events on both the tributary and the main stem at the same time, meaning coincident, and how those are related, right? So the questions we need to ask, there's two things that we need to think about. First is coincidence, meaning do things happen at the same time, right? Do the notable events or extremes happen for both variables at the same time? And the answer to that is going to define the probability descriptions of my variable A and my variable B. So if I see a flood event or an extreme on both A and B at the same time, then I need an annual frequency curve for each of the variables. It's going to be the annual maximum frequency curve for A, and not necessarily the annual maximum for B, but a value from an event. Now, if I see a flood event on A when it's just another day on B, then in that case, my probability distribution for B is going to be a daily duration curve instead of an annual frequency curve. Okay. Now, the other question is about correlation, right? If I do see notable events on both A and B, are their magnitudes related or are they independent? Now, the amount of correlation that we see is going to define the approach that we take. And so let's look at 5 different possibilities for the tributary and the mainstem relationship. All right, first is always coincident and a strong positive correlation, right? Maybe the 1% tributary event always happens with the 1% mainstem stage. This can happen with drainage areas that are small and similar in size and experiencing the same weather. So they have the same extremes at the same times. Right, the next is never coincident, right? Maybe the tributary and mainstem events never happen at the same time. Okay. Number 3 is that they can be coincident, but they're not really correlated, right? So the 1% tributary event might happen with any mainstem stage. We can have this situation when the mainstem drainage area is much greater than the tributary. So maybe the mainstem is the Ohio River and the tributary is the Kanawha. So maybe they're experiencing different weather that's driving the flows on the tributary and on the mainstem. Right. Number 4 is usually coincident, but not correlated. So we're seeing events at the same time on A and on B, but the magnitudes aren't correlated, right? So the 1% tributary event can happen with a mainstem event, but not a similar likelihood, right? And finally, we have usually coincident, but correlated, right? The correlation isn't either perfect or 0, right? That's our hardest case. Right, so conditions 1 and 2 are much easier situations, right? If we could assume variables A and B are perfectly correlated, then we're seeing the 100-year flow on the tributary always coinciding with the 100-year stage on the mainstem. Then we're just going to compute a 100-year level for variable C using the 100-year levels of variable A and B, right? That's easy. Number 2 is events A and B are never coincident. Right, so maybe the 100-year flow on the tributary always occurs with a low mainstem stage, no backwater, and that actually then has gone back to a single variable problem, right? Not multivariate, because we don't care what happens at B, right? So this is also easy. I'm just going to transform flow at A to stage at C. Right, we have to do a little bit more work with our other 3 conditions. All right, jumping right to number 5, variables A and B are usually coincident and might have some correlation, but not perfect correlation. This is the hardest case, and we will address this after, but we're going to start with the slightly easier cases. So 3 and 4 are little to no correlation, so little enough correlation that it's convenient to say independent to make our analysis a little bit easier. Okay, so here the analysis is less easy than 1 and 2, but it's still doable. It's not as bad as number 5. So in this case, the independence assumption tells us that knowing the value of B doesn't tell us anything about the value of A, right? So Greg talked about this in the multivariate lecture. Okay, so the probability of A given the condition B is just equal to the probability of A, right? Knowing B didn't tell us anything about A, right? So the difference now in conditions 3 and 4 is just going to be whether we're seeing an event for variable B or if it's just another day on variable B. Right? Now, it's easier to assume independence if we can. So we're going to go with conditions 3 or 4 with the independence assumption if correlation is below, say, 20% or some level that we feel comfortable assuming independence. But we're also going to look at the impact that the correlation has on our result. So we'll know what the consequence is on our analysis results if we assume independence as opposed to recognizing some correlation that might exist. So that's the end of the first video on coincident frequency analysis. And next, we're going to look at the total probability method to evaluate these problems.